Now, I will tell you right now. I'm telling you now. This is a hint. I'm giving you an exam hint. We are obviously not going to finish sorting and more sorting. There is a question on the exam, a non-insignificant question on the exam that has to do with this. FYI, big hint. If you're looking for more practice in the meantime, lab stuff is good. Caddis is great. But anyways, did I even start the recording? I did start the recording. Good. Sorting or balanced? I was talking about sorting. Okay, so degenerate versus balanced trees. What's the hint? Well, good thing it was recorded. You can find out later. Balanced versus degenerate, degenerate versus balanced. So a balanced tree has the property that for any node in the tree, the height of its left and right subtrees can differ by at most 1. And remember, the height of an empty tree is 0. It should be -1, isn't it? No, it's... No, it should be... Need to double check that one. So when looking here, I mean, this one's fine because the difference between the trees, like there's only 1 on a lower level than everything else. Where here, this is not balanced because, well, the left subtree, and then we've got a 1, 2, like the difference here is 2. Like we've got 2 more here than nothing. So this one, I would say, is not balanced. So in the above example, the left tree is balanced since all subtrees in the tree differ in height by no more than 1. The right tree is not balanced since the root's left subtree has height 0 and the right subtree has height 2, difference of 2. The balanced property, so all of this magic we've been talking about how like, oh, binary search is better because like if we're searching a binary search tree, if we do the naive search, where we have to look at everything, we have to do linear time work. But remember how with the binary search tree, taking advantage of the binary property, I can consecutively get rid of roughly half of the things in the tree by looking left or right exclusively. I've got that log n relationship. And we like that log n relationship. That's way better. But that all depends on having our trees being balanced. So if I added these numbers to a binary search tree, this is what the binary search tree would look like. So I had 3, 5, 9, 12, 18, 20. That's what it looks like. That would be the binary tree. Does that look like a binary tree to you? Let me ask it a slightly different way. That looks, I mean, it is, but what does this remind you more of than a binary tree? Does it look like anything else we've seen more than it looks like a tree? A stick, a linked data structure, a linked structure, right? So here, if I was looking for the number like 18, well, I start at 3, and then I would go left or right. Well, I go to the right, I go to the right, I go to the right. Here, there's no ability for me to throw away half the work or half the stuff I would need to look at in this tree. There is no, if I wanted to search this thing for something, I'd have to go down. I mean, I guess I have the benefit of like, well, okay, given that it's ordered, if I'm looking for like the number 11 and I get to 12, I can conclude, okay, it's not there. But same thing with a regular linear data structure. If I ever find an element in a sorted collection that is, I didn't find it yet, and then I get to an element in the collection that's bigger than the thing I'm looking for, I can conclude it's not there. So suddenly, if a binary tree ends up being degenerate like this, such that it's effectively a linear data structure, all of those fancy logarithmic, those order log n's go out the window, and we're stuck with a linear collection again. And we now have all these linear time algorithms instead of these fancy ones. So the above example is a very extreme case of imbalance. The particular case is called a degenerate binary tree. It's effectively a linear data structure, not a tree. So if we have a balanced tree, every time we decide to go left or right, we eliminate roughly half the elements, right? That's what gives us the log n. We are dividing by 2, divide by 2, divide by 2. And remember, in computer science, if we don't ever specify the base of the log, you assume it's base 2. So yeah, that's why I'm dividing by 2 every time. You throw away half the stuff, half the stuff, half the stuff, half the stuff. That's where we get that log relationship. So here, if I go left or right, I'm able to throw away half of the remaining things I need to look at. There's 3 over here, 3 over here. If I go to the left, I only need to look at these 3, not these 3. But since it ends up being a linear data structure, I don't get that. I don't get to throw away half the stuff. I would have to search through all elements. So any search through a degenerate tree would actually be linear, which is garbage if it's supposed to be logarithmic. Now, fortunately, there are a couple of strategies for dealing with this, where as you build the tree will self-balance. And 2 popular examples are red-black trees and AVL trees. I really don't know too much about red-black trees. When I learned this, I learned AVL trees. It's the one I always stuck with. But these binary search trees, whenever you add something to it, it's got a built-in mechanism to check for balancedness. And if it's not balanced, it will balance itself automatically to ensure the fact that we get this logarithmic relationship. The tree we built, we don't get that. That's fine for us right now because going into balancing trees is outside the scope of this course. That's getting a little too complex here. But be aware that we have a way to address this problem, but for us right now, we're not too worried about that. So any questions about the degenerate tree? Someone should submit an issue. I don't recommend making any PRs. Submit an issue to double check the height of the empty tree. Because I mean, it is going to be by how we defined it. But I believe before I said it was -1, and here I'm saying it's 1, and I just want to check out why I said 1 was one way and not the other way. Okay. Linked binary search tree. So now let's actually look at an implementation of a binary search tree, a linked binary search tree. You could build this with an array, but the linked one is perhaps a little bit more natural to think about because we're used to thinking of a tree as like, okay, we've got references to children and whatnot. So do we have any questions about what we just saw about the binary search tree before we look at the specifics of an implementation of a binary search tree? Okay. Well, here we go. And if you're following along and you open up linked binary search tree, you will find the exact same code. It's just right here. And it's downloadable. I believe there's a link at the bottom of the, linked binary search tree. You click this, you'll download the class. So we'll start with the fields and some constructors. Okay, so we want a linked binary search tree of elements of type T, but similarly with because binary search trees have this ordered property, we want to make sure that our thing of type T is comparable. In the same way that our sorted bag, the things we wanted in our collection of like the thing of type T, it's got to be comparable in some way. If the point of this data structure is to control this ordered stuff, so we need to make sure the data is orderable. So linked binary search tree, and it's implementing the binary search tree interface. 2 fields, size and root. We'll have a node called root. And then a constructor, a default one that's going to set root to null, size of 0. And then the non-default one that takes some element of type T, it calls this, which means call the default constructor, and then immediately add the element. Now, we haven't looked at the add method. We'll look at the add method right here. But yeah, we call the constructor and then just immediately add something to it. What does super? So that means that the thing that's comparable, the thing of type T doesn't need to be comparable, but it or one of its superclasses, one of its parents, one of its ancestors must be comparable. That's all. If you hate this, just you can ignore this a bit. You can ignore question mark super T because it's now extra fancy details by having question mark super. You could just think, you can pretend it doesn't exist for the sake of understanding this. Now, one thing I want to emphasize here is node of type T. Now, you might be saying, well, hold on. Nodes, those were like the singly linked nodes. And you're right. When we did build the node class before, we had it have like data and next. But we know with binary search trees, we need a left and a right. But why are we creating something of type node? Well, you may remember from months ago now that, well, we've got two choices for where we're going to put the node. Like, how are we going to deal with the node class? We can create a top level node class. That would be something like going into source, main, creating something like a binary node, right? There we go. But the problem is, like, you know, for a given link structure, we always have nodes. Why'd I close these? Come on. We always have nodes and whatnot. So, you know, node is a far more general word. When I say node, the natural question you ask is like, well, if I don't know the context, is it a doubly linked node? Is it a singly linked node? Is it a binary tree node? What is it? So our nodes are very context sensitive. When I say node in the context of a binary tree, you go, okay, so it's the thing with a left and a right. When I say node in the context of a queue, look, there's a period. Someone can go make a PR to get rid of this period. Right there. Yeah, so when I say node into something like a linked queue, you're going to think, okay, it's a singly linked node. So node is far more general. And the problem is I can't have a bunch of different classes in my project called node. I can't have a node that's a singly linked node and a node that's a binary node, right? I would have to give it another name. I can't have two classes with the same name mean two different things. Unless you make them internal classes, meaning we're defining the class, but the class only exists within some other class, and it can't be accessed elsewhere. And this is going to make a lot of sense for us because our binary node is only, like the nodes for this binary tree are only used inside this linked binary tree. This is the same idea that you see in assignment 4, right? In assignment 4, I had, wait, did I? What did I give you? No, it was for the priority queue, I believe, right? For the priority queue, I gave you the internal node class, but it was called like priority node or something, right? Is that right? I'm trying to remember. I think that's right, but no one else seems to remember either. So anyways, I made it a private static class node. Meaning, great, I've created this class. It's called a node. It's private though. So like it only exists inside this class. So what's the node? Well, it's a binary tree node. It's exactly the same as this binary node. Data, left, right, constructor, get data, get set data, get left, get right. It's the same. It's just, it's written inside here. So now whenever I say node, it's referring to the node that's within this class. So the class itself is private, but it's contained within the linked binary search tree. And if you don't remember, there was an aside on this for topic 8 ages ago that I'm sure you all looked at. So you all know this already anyways. All right. So to keep things clean, we're going to go with option 2. We create this private static node class. Things of note for this node class, it's a binary tree node. The nested static class is contained within the linked binary search tree class, just like you see here. All right, so we've got our fields and our constructor. Great, we want to add something to our binary search tree. How are we going to do it? Okay, we'll create our public-facing interface method, the add one, that just takes an arbitrary element t of type t, and we're going to add it. And we're going to call some private method add that takes some other attribute or some other argument I'll talk about in 1 second. And then after that's done, we increase the size. Great. Makes sense. So add is, okay, just go magically add. And then once you're done, add 1 to the size of the tree. Makes sense. Now let's have a look at the private one. And I'm going to tell you, this is a recursive method. And I want you to take special note that this method, this add method, actually has a return type of node. So we take the element, add the element that we want to add, and then some node we're going to refer to as current. And the first time it's called, you'll see that it starts at the root. So let's see what happens. So if current is null, well, if we're ever null, like let's say the root. Let's say there's nothing in this tree, so the root is null. So let's think about what this would mean. Root, well, that's null. We're calling this method add. Okay, so if current's null, that would mean the root is null. Create a new node with that element in it. There. And then we return that new node. That's, you know, the thing being returned of type node. And then after calling add, I mean, this returns that node, so root is set to, well, that new node we just created. So this checks out, right? But if current is not null, meaning, okay, that node exists, great. So if I'm looking at the root and its number is 55, but the thing I want to add is less than that, well, I should go to the left. If it's greater than 55, I should go to the right. So that's what these two are right here. These are where the recursive calls come into play. So if the current's data compared to element is greater than 0, basically meaning if the data at the node is bigger than the thing I want to add, it goes to the left. Otherwise, it goes to the right. Okay? Then what am I doing here? Okay, so I'm saying current, so root. Let's update your left. So let's say the root doesn't have. So I'll draw it now. So we've got, let's say the root exists, and the root has a left and a right that may or may not be null. This is root. But for now, we're calling this current. Okay? Current exists. We already dealt with the current as null. So I say, okay, let's say I want to add the number, this is 55 in here, and I want to add the number 40. So I'm saying, okay, current, set your left to whatever is returned by add the element on the current's left. So what does that mean? Okay, so we're calling add with the element, and then current becomes current's left. So, okay, now the next time I'm going to use a green one. C is pointing to this now because it's the original current left. So now we create a new call frame. We start the method again, and I ask the question, okay, is current null? It is. Okay, great. So now I'm going to create a new node and put the element in there. What did I say? 40, I think. So I'll put a 40. Great. And then once I'm done, I return that node. So that node gets returned to right here. And what are we immediately doing with that new node that gets returned? Well, we're setting it to the previous current's left. So, hey, this current here, your left is now that new node that just got created by that recursive call. If, let's say, that node did exist, let's go down one more level. Okay, so we started here, and then, okay, current was this, 40. And now let's say I'm adding the number 30. So we start the first level, is current null? No, but the thing I want to add is less than, so we go to the left. Okay, is the current null now? No, but the thing I want to add goes to the left. Okay, great. So we go down another recursive call, and current would be this one's left. So I say, okay, current is now null. Okay, so I create a new node. Okay, create a new node, put the number in there. I think I said 30, right? And then I return that new node. Okay, then I return to the calling function, which was this one, when current was the root's left. And I'm saying, oh, okay, so set your left to this new node. Great. Then I finish these if-elses, and then I return current. So, okay, so current's left was just set to that new node. And then I return current. So I return a reference to this node, to the calling function, which was, or the calling one, which was when current was root. And we are saying, well, we just finished calling the add, and that returned the current, which was your original left. Just set your left to what it just was. What I have a feeling that we are now at the stage of experience with programming that when I am explaining this function in English, it's harder to follow than just looking at the code and working it out with pencil, paper, and drawing it and convincing yourself. It's getting to the point where you have the skills and understanding of the code where my actual English explanation of what's happening is kind of hard to follow compared to what you could do if you just took this, executed it, tinkered with it, and understood it. So that's the best way to learn this stuff. You learn by doing. So let me explain here. Okay, we use the helper method to set up a call to the recursive method. The method is very similar to the binary search. Keep going left, right, down the tree based on the ordering of the order of the tree and the value of the element being added. As soon as you find an empty spot, insert the node. Inserted value will be in a leaf node spot. Great. Any questions about that add? I won't be surprised if you have any, so feel free to ask. Very thirsty, though. All right, well, if you do, throw them in the chat. Maximum and minimum. We already kind of looked at these last time. Min, well, if the tree's empty, throw an exception. Otherwise, call min on the root. So we've got this public min that doesn't take any arguments. And now we've got this private recursive one that takes some given node. So we start at the root. Hey, root, you exist because it's not empty. So, hey, root, does your left child exist? Because if you have a left child, that left child has a value that must be less than you, given the definition of a binary search tree. So if your left is null, you, current, must be the smallest element. If your left is not null, that means there is a node to the left of the current that is smaller, that has data that's smaller than you. So look for the min on that one now. So I would go to the left. I would call it not on current anymore, but current's left, and then say, okay, hey, new current. What's your left? Do you exist? Repeat. And the exact same thing with max, except instead of going to the left, you go to the right and you check the right. You could write these iteratively, but I don't know. These recursive ones are just so simple. If current's right doesn't exist, I now know current is the rightmost thing. Return the data. Otherwise, call max on current's right. It's like saying, if I have some tree, the largest element would be in here, right? It's got some value X. But if I'm looking at this and say, hey, current, do you have a right? Yeah, okay, then just look for the max on your right. Okay, current, do you have a right? Yeah, okay, look to the right again and find the max on your right child. Okay, there we go. Hey, current, do you have a right? No. Oh, well then you must therefore be the biggest number, so just return your data. There, max. Again, remember I was warning you, recursion's about to take over. Because writing these functions, or methods, pardon me, get a lot more tedious if you're doing it with loops. These recursive ones are just so nice and simple, clean. Fortunately, minimum and maximum are simple. Due to the order in each of the binary tree, just go all the way left or right to find the minimum or maximum value. Remove min and remove max. Now, this is where things got a little different, right? Because we had those three cases where it was the root, where it was a leaf, or where it was an internal node. Meaning, like, if I'm removing the min, then it must have a right child. But then we also did see that the three cases were kind of exactly the same. The rule was, replace it with the node's right child, right? Because, let's go, remove the minimum. If the minimum's 9, you just remove it and replace it with 9's right child. Well, 9's right child is null, so 15's left becomes null. See? Now if I'm removing 15, okay, remove 15 and replace it with 15's right child. Well, that's the 18. Boom, there. And now if I wanted to remove 26, which is the minimum, I replace it with the node I'm removing's right child, which is the 38. So even though we had three cases, they're actually all addressed the exact same way. So if we want to remove them, let's say we're removing the minimum. Well, I've got a public facing one that just takes no arguments. And then this one that has two parameters, okay? The one that takes current and the current's left child. So how are we going to start it? So the public facing one is, we start with some return element that's null. If the tree is empty, throw an exception. There's a no such element exception. Else if roots get left is null, then all I need to do, like this is kind of like case number 1, right? Where it's the root node. So if roots left doesn't exist, I can just replace the root with its right child. So I just say, okay, root, you're now equal to root's right child. Done. Otherwise, we call the recursive one. Okay? So the recursive method returns something of type t, the element we're removing. Now let's have a look. It takes current and it takes left child. So the first time we call this, we say remove min on root, where root is the current and root's left child is root's left child. The left child is the left child. So let's see what we're saying. Now, if the left child's left is null, current, set your left to the left child's right. Return left child's data. Otherwise, recursively call it again on current's left and the left child's left, which would be current's left's lefts. Right? That's it. So this one's kind of interesting because it passes along two references that get updated every time we do a recursive call. But really what it's doing is if we have a tree, so let's say I was doing the remove max, so I'm going down the right side. The first time I would call it, this would be current, this would be right. Then if I did another recursive call, well, whoop. This would be current. This would be right. So we are updating two reference variables here, the two parameters, every single time we call this. And we just keep track of the parent and its left or right child, depending if we're moving minimum or maximum. But we keep track of the parent and left. And the reason we want to keep track of both is because, well, the current's new left needs to be replaced, if it's being replaced, needs to be replaced with its left child's right. So we do need to keep track of a couple of extra things there. You could get fancy and do it with one reference, but it's going to be a lot grosser. So this one here, this implementation's pretty nice and clean. So any questions about removing min or removing max? All right. Yeah, okay. This is just explanation. Remove max. So here's a remove max that's iterative. So we could implement it the same way, but here's an alternative idea. It's iterative. Okay. If it's empty, whatever. Okay. If roots get right is null, roots is now left. Otherwise, we've got parent is the root, right child is roots right. While right child's get right is not null, parent equals right child equals right child dot get next. So the right child's right exists, keep moving, down that tree. And then once you're done, you get the data, and then you set the parent's right to the right child's left. Again, this is because we're removing the maximum, so, it's the mirror of removing the minimum. So here's a way to do it iteratively. And there's nothing wrong with this. But I don't know, this nice little recursive one right here is nice and clean. And, where this one, there's nothing wrong with the while loop. It's not bad. And, arguably it's nice and clean too, but, different. Two sides of the same coin. Now, the general remove. This is the most complex function we're going to discuss. So, I'm going to break it down into bits. So, the public remove method is similar to the public remove min and remove max. It checks if the root node to see if its value is to be removed. Otherwise, it checks the subtrees to continue searching down and calls the recursive private remove. So we're going to recursively search for the thing we want to remove. But remember, when we removed something, we had to deal with that case of replacing it with its immediate predecessor from a pre-order or an in-order traversal, or its immediate successor from an in-order traversal. So either the biggest value in its left subtree or the smallest value in its right subtree. So the smallest, bigger value. So public remove, and then I've got the private remove. And there's also another helper method here called find replacement node, which is right here. And we're going to look at all of these. So the public remove. Start with the thing we're going to remove being null. If it's empty, throw an exception. Else if the root's data is equal to the thing we want to remove, well, then we get the data from the root, save it, to be returned later down here. And then root is going to be equal to the result of find replacement node. So we need to magically find a replacement node. But assuming that that function exists, replace the root with its appropriate replacement node, and then we're done. Otherwise, if the data that we're looking for should be removed, if the data that we want to remove should be to the left, we will now call the private remove, the recursive one, on the left subtree. Otherwise, call it on the right subtree. And notice that it's going to be similar in the sense of the remove min and remove max, where we take the root and the left child. Or we have a current and then the current's left child, where the first time it'll be current will be root, and the current's left child will be root's left child. So this is the recursive one. So if we carry on this idea to the recursive one, what do we see? If child is null, no such element exception. So if we ever get to the end, if we ever are trying to remove something that we're searching for, and we find a leaf node that doesn't exist, meaning let's say I've got a tree where this is 12, this is 20, and I say, hey, remove the number 7. Well, the number 7 should be here, but if I'm doing a binary search for the 7, the thing I want to remove, that's what we're going to do to find the thing we want to remove. If I go down here and say, hey, does this right here, does your left not exist? Basically, the 7 should be to the left of you, 12, but you have no left child, which means 7 must not be there, meaning, uh-oh. So it's not there. So we throw an exception, the no such element exception. We're trying to remove something from the collection that just doesn't exist. Otherwise, if we found the thing we want to remove, well, we find the replacement node. And we set the parent's left to the replacement node. Else, replacement node to the right. Oh, pardon me. Otherwise, okay, if it equals the element, if parents get data compared to element, if child's data, well, now I'm confused. Is it the end of the semester yet? If child's get data equals element, so if we find the thing we want to remove, if the parent's data is greater than, oh, okay, so this is saying which one is getting removed, the left or the right. We find the replacement nodes, return the child, that's the thing being removed. Parent, child, yeah, so we're removing the child. Otherwise, child compared to, if the thing we're looking for should be to the left, continue searching down the left. If it's to the right, continue searching down the right. So the same general principles are there, where we just have these two references that are moving down the tree as we search for the thing. It's just we might end up going left or right, not just always left or always right when looking to remove the minimum or the maximum. So we're doing a binary search down for the thing we want to remove, and then as soon as we find the thing we want to remove, we need to get rid of that child, get rid of the thing we want to remove, but replace it with a replacement node. And that's where this final helper method pops up. There is a lot of code here, but it's actually not a lot. So replacement node starts at null. If 2 removes left is null, and 2 removes right is null, the replacement node is null. This means it was a leaf node. If the thing I want to remove doesn't have a left or a right, there's no leaf. So there's nothing worth replacing it with. If 2 removes left is not null, but its right is, well, that's easy. You just replace it with the left. Similarly, if its left is null, but its right's not, we'll just replace it with the right. Now we've got the funny case where, okay, we now have an issue where I guess both left and right aren't null. Okay, so now we need to find the in-order successor, right child's leftmost node, minimum node. So this is just going to do that search. So child get left if it's not null. Okay, you set up the search. Child set left to remove get left. And then you do the search for what you're looking for in the same way that you did the minimum. Last minute of the semester. I'm sorry, guys. I know you love me that much. This is just the explanation. Contains, it's just a binary search. Get count, it's a binary search, except this time you also just continue adding numbers together. And that's that. Don't worry, linked binary search trees. There is something on the exam about them, but you're going to be using them, not implementing them. And the one you're going to use is the one I gave you. So you don't actually have to like implement it. You just need to know like add, remove, and the methods that exist in it. Cool. Any final questions before I say goodbye to you forever? Oh yeah, no lab tomorrow. F that. Okay. I'll set an email up too. I will say it's concerning. Only 20 people here of the like 50 or whatever that are supposed to be here. Office hours tomorrow? Yeah, there'll be office hours tomorrow, but those will be the last ones. So you'll miss me. I know. You are loyal. You are the loyal ones. You're right. It's not forever. You're right. See you later at 2:15 if you're there. Yeah, see ya. All right, everybody. I'll see you later. Enjoy the rest of your day, and I'll see a bunch of you later today.